Ethernet networks in review. Ethernet is a contention-based media access method that allows all hosts on a network to share the same bandwidth of a link. Ethernet is popular because it's readily scalable, meaning that it's comparatively easy to integrate new technologies, such as upgrading to fast Ethernet to gigabit Ethernet into an existing network infrastructure. It's also relatively simple to implement in the first place, and with it, troubleshooting is reasonably straightforward. Ethernet uses both data link and physical layer specifications, and in this chapter we will give you both the data link layer and the physical layer information you need to effectively implement, troubleshoot and maintain an Ethernet network collision domain. As mentioned in chapter 2, the term collision domain is an Ethernet term that refers to a particular scenario wherein one device sends a packet out on a network segment, thereby forcing every other device on that same physical network segment to pay attention to it. This can be bad because if two devices on one physical media segment transmit at the same time, a collision event, a situation where each device's digital signals interfere with one another on the wire, occurs and forces the device to retransmit later. Collisions can have a dramatically negative effect on network performance, so they're definitely something you want to avoid. The situation I just described is typically found in a hub environment where each host segment connects to a hub that represents only one collision domain and one broadcast domain. This begs the question that we discussed in chapter 2. What's a broadcast domain? Broadcast domain. Here's a written definition. Broadcast domain refers a group of devices on a network segment that hear all broadcasts sent on that network segment. Each through a broadcast domain is typically a boundary delimited by physical media like switches and routers. It's also a reference a logical division of a network segment where all hosts can reach each other via a data link layer hardware address broadcast. That's a basic story. So now let's take a look at a collision detection mechanism used in half-duplex Ethernet, CSMA CD. Ethernet networking uses carrier sense multiple access with collision detection, CSMA CD, a protocol that helps devices share the bandwidth evenly without having two devices transmit at the same time on the network medium. CSMA CD was created to overcome the problem of those collisions that occur where packets are transmitted simultaneously from different nodes, and trust me, good collision management is crucial because when a node transmits in a CSMA CD network, all the other nodes on the network receive and examine that transmission. Only bridges and routers can effectively prevent a transmission from propagating through an entire network. So how does CSMA CD protocol work? Let's start by taking a look at figure 3.1. When a host wants to transmit over the network, it first checks for the presence of a digital signal on the wire. If all is clear, meaning no carrier is present, no other host is transmitting, the host will then proceed with its transmission, but it doesn't stop there. The transmitting host constantly monitors the wire to make sure no other host begins transmitting. If the host detects another signal on the wire, it sends out an extended jam signal that causes all nodes on the segment to stop sending think busy signal. The nodes respond to that jam signal by waiting a while before attempting to retransmit again. Back-off algorithms determine when the colliding stations can retransmit. If collisions keep occurring after 15 tries, the node attempts to retransmit will then time out pretty clean. So here you can see figure 3.1 CSMA CD, carrier sense multiple access with collision detection, CSMA CD. When a collision occurs on an Ethernet LAN, the following happens. A jam signal informs all devices that a collision occurred. The collision invokes a random back-off algorithm. Each device on the Ethernet segment stops transmitting for a short time until their back-off timers expire. All hosts have equal opportunity to transmit after the timers have expired. The following are effects of having a CSMA CD network: sustaining heavy collisions, delay, low throughput, congestion. In the following sections, I'm going to cover Ethernet in detail at both the data link layer, layer 2, and the physical layer, layer 1. Half-duplex Ethernet is defined in the original IEEE 802 Ethernet specification. Cisco says it uses only one wire pair with a digital signal running in both directions on the wire. Certainly the IEEE specifications discuss the process of half-duplex somewhat differently, but what Cisco is talking about is a general sense of what is happening here with Ethernet. It also uses the CSMA CD protocol to help prevent collisions and to permit retransmitting. If a collision does occur, if a hub is attached to a switch, it must operate in half-duplex mode because the end stations must be able to detect collisions. Half-duplex Ethernet is only about 30 to 40% efficient because a large 100 base TX network will usually give you 30 to 40 megabits at most, but full duplex Ethernet uses two pairs of wires at the same time instead of one wire pair like half duplex. And full duplex uses a point-to-point connection between the transmitter of the transmitting device and the receiver of the receiving device. This means that with full duplex data transfer, you get a faster data transfer compared to half duplex, and because the transmitted data is sent on a different set of wires than the received data, no collisions will occur. The reason you don't need to worry about collisions is because it's like a freeway with multiple lanes instead of a single lane road provided by half duplex. Full duplex Ethernet is supposed to offer 100% efficiency in both directions. For example, you can get 20 Mbps with a 10 Mbps Ethernet running full duplex, or 200 Mbps for fast Ethernet, but this rate is something known as an aggregate rate, which translates as you're supposed to get 100% efficiency, no guarantees in networking as in life. Full duplex Ethernet can be used in the following typical situations: within a connection from a switch to a host, with a connection from a switch to a switch, with a connection from a host to a host using a crossover cable, with a connection from a switch to a router, with a connection from a router to a router. Now, if it's capable of all that speed, why wouldn't it deliver well? When a full duplex Ethernet port is powered on, it first connects to the remote end and then negotiates with the other end of the fast Ethernet link. This is called an auto-detect mechanism. This mechanism first decides on the exchange capability, which means it checks to see if it can run at 10 Mbps, 100 Mbps, or 1000 Mbps, or even 10,000 Mbps. It then checks to see if it can run full duplex. If it can't, it'll run half duplex. Last to remember these important points: there are no collisions in full duplex mode. A dedicated switch port is required for each full duplex mode. The network card and the switch port must be capable of operating in a full duplex mode. Ethernet at the data link layer. Ethernet at the data link layer is responsible for Ethernet addressing, commonly referred to as hardware addressing or MAC addressing. Ethernet is also responsible for framing packets received from the network layer and preparing them for transmission on the local network through the Ethernet contention-based media access method. There are 4 different types of Ethernet frames available: Ethernet 2, IEEE 802.3, IEEE 802.2, Sub Network Access Protocol SNAP. I'll go over all 4 of the available Ethernet frames in the upcoming sections, but it's important to remember that networks typically use only Ethernet 2 frame today, but the CCNA data center objectives cover all 4. Why talk about frames that we don't use? That's a good question. My only thought is special Cisco Torture SCT. Seriously though, for Ethernet we use only Ethernet 2, but the current wireless specifications do use a SNAP frame. I'll show you that frame in a minute, and it's an exam objective. Ethernet addressing. Here's where we get into how Ethernet addressing works. It uses the media access control MAC address burned into each and every Ethernet network interface card NIC. However, this address can be overridden. The MAC or hardware address is a 48-bit 6-byte address written in a hexadecimal format. Figure 3.2 shows the 48-bit MAC address and how the bits are divided. The organizational unique identifier OUI is assigned by the IEEE to an organization. It's composed of 24 bits or 3 bytes. The organization in turn assigns a globally administered address, 24 bits or 3 bytes, that is unique. Supposedly, again, no guarantees to each and every adapter in manufacturers. Look closely at the figure. The high order bit is the individual group IG bit. When it has a value of 0, we can assume that the address is the MAC address of a device and may well appear in the source portion of the MAC header. When it is a 1, we can assume that the address represents either a broadcast or multicast address in Ethernet, or a broadcast or functional address in token ring or FDDI. Figure 3.2, Ethernet addressing using MAC addresses. So see here, 24 bits, 47, 46 IGGL, organizational unique identifier OUI assigned by the IEEE vendor assigned. The next bit is a global local bit, or just GL bit, known as UL, whereas U means universal. When set to 0, this bit represents a globally administered address as by the IEEE. When the bit is at 1, it represents a locally governed and administered address. The low order 24 bits of an Ethernet address represent a locally administered or manufacturer signed code. This portion commonly starts with 24 zeros for the first card made and contains in order until 24 ones for the last 1677216 card made. You will find many manufacturers use the same 6 hex digits as the last characters for their serial number on the same card. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.